Good morning and good afternoon. Today we are going to solve some additional interesting problems on dry friction, static equilibrium problems, where we were done earlier some very interesting problem, right? I'm going to continue with that, just quickly looking at what are the problems that we solved in the last class, and we'll add some additional problems so that again to confirm our understanding of theory of this Coulomb friction. So for that purpose, let me share my screen. Hope you are able to see this ActivInspire board.
Yes, sir.
Yeah. So we had, this is our third lecture on, today's lecture is the third lecture on dry friction topic, module 3. So we have learned the theory of dry friction, and this slide is an evidence for that. Then we had solved some, we have looked at some interesting experimental trials, virtual trials, having this platform which can be rotated. So we understood importantly, important definition called angle of repose, right? Also, we were able to differentiate between tipping and sliding, and we are able to have the conditions necessary for tipping and sliding. So this learned theory is what we have applied on some problems, and we were able to solve. So on lecture number 21, we had this interesting problem of two blocks where their contact surface coefficients are coefficient of dry frictions are different. So what would happen if they are to impend down? What is the angle theta required is what we have found. At that time, what would be the tension in the cable? Also we have calculated, and I had given you a homework that what would happen if you vary this angle theta and the tension value. I hope you are done that, and please do and have an observation if you have not carried out, right? And then another interesting problem that instead of a block, if we have a drum, why do I call that as a drum? Is because the dimension of the height compared to that of the base is more, and there can be a chance that before the sliding to happen, this drum can rotate or tip about the leading edge. So we were able to solve this problem. I had also given you to investigate. In case I give you mu s instead of 0.55 in this problem, if you have 0.1 or 0.2, so the scenario can be different. So that's what I was telling. So then sliding may occur before tipping to occur. So you could have done and made that understanding as well. So today's class, I'm going to give you some example problem. Again, those problems are interesting problem to confirm your understanding of this topic, right? Just a minute. Under this board. So this is lecture number 23, and today's date, sorry, 22, right? 22, and today's date 2/4/2021. Let us have an interesting problem. See, there are a lot of basics of statics that we have learned that we are going to revisit in these problems, and it's going to be very interesting, right? So the first problem we have looked at in previous days problems, a block or drum on the slope. I'm going to draw a cylinder on a slope. So what would happen? Let's look at and then understand the role of dry friction there, right? So that is the objective of today's class. See, I have a slope now. The slope angle is theta. And instead of a block, I have here a cylinder. right? The contact is lost here. Just a minute. Consider there is a cylinder. So this cylinder is of diameter 2 meters, let's consider, and the weight of the cylinder is 100 Newton, right? And it's a homogeneous cylinder, so I take the section plane, cross-section plane at its CG. So the cylinder is represented as a circle now in my diagram. So here, let's represent the weight of the cylinder, W. Now, what would be the free body diagram? So I will have here a normal. And I would also have here a force. What is the direction of the force that we expect? Friction force?
Back side, sir. Towards the left side.
Like this, down or up?
Upwards.
Upwards.
Upwards. Okay. So this is the direction of friction force there. Right? So now this cylinder is resting on the slope. If I say, do you agree on it? The cylinder diagram, it is not under static condition. So what is the state of the cylinder? If I ask, what would you say? Answer, that is not staying there. It is rolling down, you would say, right?
Yes, sir.
Yeah. So when it will be rolling down, when this friction force is lesser than the maximum static friction value, then only it will be rolling down. Supposing if it is more, then more means it is equal to μs times n, then it would be, instead of rolling, there will be slip here, there will be sliding here. So sliding and rolling cannot take place simultaneously. Either the cylinder slide or roll, like that it will go. So the condition for rolling of the cylinder down the slope, where this friction F should be less than μs times n. That's an important condition for rolling of the cylinder down. Right? So now the question is not dynamic state, rolling state of the cylinder. So I have to arrest this rolling and make this is stationary. So what I would do, I would take here a block that I attach. So I can keep increasing the weight here. There is a rope goes around this, and then I can keep increasing this value of P, right? So at one point of time, the cylinder is under rest condition, right? So when I attach this load P, this is under rest condition. This is under rest condition. So now, what is the question is? What is the question is? This. If slipping means instead of rolling, if sliding to impend, right? For sliding or for slipping, the word is slipping here, right? If slipping to impend, if slipping to impend, what is the value of mu and P? If slipping to impend, determine values of mu, S and P. That's the question. Do you get the question? So the cylinder is under rest condition now. So earlier I had not drawn in my configuration this cable and the load attached. But now the cable and the load P attached is there, and I could say this is in rest condition. That means static equilibrium condition. Static equilibrium state. Static equilibrium state. Now I have to disturb the static equilibrium state and it has to roll. That is what is an impending state. If slipping to impend, this is the question. If slipping to impend, right? Determine the value of μs and n, μs and P. That's the question. So how can you find out that? What is the value of it? Can anyone answer? Or do you have understood the question that I asked? Any doubt in that? Pranesh.
Sir, F will need to be great.
F is?
F should be greater than mu SN for sleeping.
Yeah, that it cannot be greater because mu SN is what is the maximum value possible, right? This is maximum value possible.
Sir, it should be equal to.
This is the maximum friction that can be developed at the contact. So how can F will be greater than that? It cannot go greater than that.
Yes, sir. Yes, sir. Yes, sir. Yes, sir.
So if it is less than this, there is a rolling state if P is not there. But P is there, so it is in rest condition. So it should go to an impending state. That's why less than or equal, I should say. So when F is equal to this, what would happen? It has gone to the state of sliding. So this slipping. So then this F is going to be mu s times N. Right? That is one thing. If you look at any rolling wheel down, then the friction force, if you look at, it would be not in this direction, it is along the translational direction of its center. That is in a rolling state, right? So whatever we look at is in rest state, rest condition or impending condition in this problem. Supposing a wheel is rolling down, if you say, then the direction of friction is not up, it is in the forward direction. So best example is when you drive the car, the traction that is acting at the contact of the tire with the road, the tractive force is forward direction. Because when it is rolling, the rolling of this to be resisted, then friction direction would be like that. But now this cylinder what is drawn is under rest condition. So when it is under rest condition, then there is no motion. So the friction direction, what you have at the beginning said is correct, right? So that is all the clarity that you should have. So we had three states. One is rest. Second state is impending to slip. Third state is rolling motion. So rolling down. So when it is rolling down, then the friction direction would be different. So to roll down, then I should cut this cable. So this will be rolling down. As it starts rolling, what would happen? The direction in this free body diagram F shown would be reversed. And that value of F would be Fk is equal to mu k times N. Right? This is all that you should understand. But now in our today's problem discussion, we are not going to look at this state. We don't want this. We are working the data given and this problem asked for the rest condition to impending to slip condition. So impending to slip condition means this value of F should reach to mu s times N. Rolling condition means the friction force is reached this and beyond that, and you have your friction called mu k times N, kinetic friction force then, right? So this is all the clarity that you should have. Now, why did I choose this problem? Is this very interesting problem. Why? 3-force equilibrium is what is that you have to understand. We have looked at 3-force equilibrium in our first module. So can you say what do you mean by 3-force equilibrium?
Lam's theorem.
Lam's theorem is used to solve a 3-force equilibrium. That's fine. So what do you mean by 3-force equilibrium? What is the condition for 3 forces to make a free body diagram of the system under static equilibrium?
So they shouldn't be parallel. They should
correct.
be concurrent.
Three non-parallel forces, if they make a system, then it can be called as a 3-force equilibrium.
Yeah, 3-force equilibrium is one of the fundamental concept of statics. 3 forces equilibrium means the 3 forces should essentially concurrent. System of forces, right? In the free body diagram, or they should be parallel. Remember? So what is the best example of 3-force parallel equilibrium? Passenger car which is parked, which is not moving, which we have looked at, right? If we take this car, the weight is acting down and the support reactions in both the wheels are there here. This is its free body diagram. So this is front axle load and this is rear axle load and this is W. So look at these three are parallel force system. So 3-force equilibrium. So other example of concurrent system forces is whenever there are 3 forces in free body diagram, 3 forces and that body is under equilibrium, there should be concurrent system of force. That is very common, evident. We have solved many number of problems. And friction, wedge friction problem, you'll see that is quite useful approach to solve, right? So why did I bring this point again here is look at now this free body diagram carefully. So I have how many forces? I have this force W, weight, and I have this, if I cut this, I would have P, load P. So P and W are parallel. So what is my third force? The reaction at the contact. So what is the reaction at the contact? Resultant of normal and this friction force. And that should be essentially parallel, right? That's the reaction. So these two, P and W are parallel, R also should be parallel, then only this can be under equilibrium. If P and W are intersecting, then R should be also intersecting the point, that is for the case 1. So this condition is what is imposed from your fundamental understanding of 3-force equilibrium. So W and P are parallel, so the reaction should be vertical here, parallel to these two. So if this is so, now what is this angle? Angle phi, which is equal to theta as well. So this will be phi s when F is Fs. So that is that the second question asked, impending to slip. So impending to slip, this free body diagram, this will be Fs and this is my normal N, and the resultant of that is reaction R, that should be parallel to P and W. That's it. So now that says this angle here, what is normally defined as friction angle, should be same as this angle theta, as normal will have to the vertical angle theta. So this condition is coming. So this all are just to understanding this concept. So when this is so, in your problem, if theta is given in your problem as 30 degrees and you are asked to find out this, you would straight away get what is mu s value. So mu s value will be tan inverse of 30 degrees. So that's going to be 0.577 answer, right? So this is very interesting problem. You can also prove this through the equations. You can also prove this by the equations. How do you do that? So you can develop the equations. So what are the equations? Let us consider this center of the cylinder point O, and let me take moment about point O. Right? If I take moment about point O, this normal will pass through that and W passes through that, that won't participate in the equation. So I will have my F. So I will consider as friction force instead of Fs. And I'm going to take that as theta. So that is in rest condition. So F into R is what is P into R, because P is also tangential here. So F is equal to P. So first equation, when I apply moment balance equation, M naught equal to 0, I would have the condition F is equal to P, right? That's my equation number 1. So having the second equation, sigma Fi equal to 0. So what is my y direction here? I'm going to consider my y direction as normal direction to the slope. This is y and this is x. And I'll take this positive convention. Down x is positive, up y is positive. So this is the convention if I follow. Now I can write this equation, sigma Fy equal to 0. So what is that I will have? So here this angle is going to be normal theta. So I would have here W cos theta. I have here P. This is tangential again here. So if this is tangential, so what is this angle? This angle, if I draw from here a tangent, this contact point like this. So this angle also is 30 degrees. So I would have here my second equation would be N up positive minus P cos theta plus minus W sin theta. So P plus W within bracket cos theta equals 0. I would have my normal value is P plus W cos theta. Right? That's equation number 2. Now what is my third equation? Having third condition of equilibrium, sigma Fx equals 0, considering this positive, here this positive, here counterclockwise positive. This convention always put, that's a good practice. So what is that I will have here? I would have P plus W within bracket sine theta, right there, horizontal component along the slope sine theta minus F, that's opposite to this 2, and that's equal to 0. So I would have my friction force equal to P plus W sine theta, right? So this is my third equation. So now the conditions that you know, right, for impending to slip, for impending to slip, condition is F should be equal to mu s times N. So substitute now in this. So F is W sin theta, P plus W sin theta. That's equal to mu s times what is N? P plus W into cos theta. So now here I have P plus W goes off. So I would get tan theta is what is mu s. So theta here given in the problem is 30 degrees. So mu s would be so mu s is what is tan theta. Right? Tan theta is equal to mu s. So mu s is tan 30, which is equal to 0.5774 value. So this is how also you can solve. So if you are not applying this condition, that it should either be concurrent or parallel. So if it is parallel, without writing this equation, I was able to comment that the resultant of these two R should be parallel to this. Hence, this angle should be theta equals phi s. So I was able to answer this straight away. That is our understanding of 3-force equilibrium. Supposing that doesn't click to you and you want to systematically do by writing the equation, you consider the friction force at the moment is not reached to the maximum value possible. Consider as F and P, and then this is balanced from the free body diagram. And then you write down this equation in this manner and say, then impose the condition for impending to slip, this F should be equal to this, and then you solve, you get the same answer. So this all does that interesting aspects of our mechanics course. Any doubt in this problem? Do you want to ask? Any doubt?
No, sir.
Ravi Shankar.
No, sir.
Any doubt? Do you have?
No, sir.
No. So shall we proceed to the next problem?
Yes, sir.
Yes, sir.
So now another interesting good problem. I'm going to take again a block on slope, right? I'm not going to give a data. Let's work out this. There are a lot of interesting aspects. Theta, I have a block here, which weighs W. Now, I have this block kept here. If I say it is not staying, it is sliding down. So what is the condition? What do you mean by that? If I say that block, now the state of the block is moving down, when I say, what is that answer that you'd say?
It is in motion.
Yeah, if I say, see, when I put the cylinder, you are able to say immediately it is rolling down. But now I have a block here, right? If I have a block here and I say this is not in rest condition, this is moving. That means what do you comment on this configuration with respect to this angle theta?
Theta would be greater than or equal to the angle of repose. It will be greater than angle of repose.
Angle of repose, right? It is angle of repose, it is that impending state. If block kept here is sliding down, if I say, what is this angle theta? If I ask, you should say it should be greater than angle of repose. Excellent. You have correctly answered. So any angle slope which is greater than angle of repose, where angle of repose by magnitude equal to friction angle between the block and the slope that you have learned, would happen. So if this theta is greater than friction angle here, then this block will slide on its own, right? So that is the state now, if you assume. To stop this, I require a force. So I require a force P, and that force P I am going to apply at in this direction. So there is a force P now to hold this not sliding down. Very interesting, right? So this is applied at an angle alpha to the slope, right? So this is not now sliding. But now assume that if I keep this P value is not just to holding this not sliding. If I keep increasing this magnitude, what would happen to this block?
Sir, magnitude of P, sir?
See, you understood. I introduced P now. Why? Because when I say this theta is greater than angle of repose, the block will slide on its own. I want the state of rest condition. So I apply a force P at an angle alpha here. So that now it is not sliding, it is staying. So that means what? It is holding this, not sliding, right?
Yes, sir.
Yeah. But the magnitude of P, which is just holding, if I keep increasing, what would happen to the block?
The block will move upwards.
Yeah, there is a point when block can move upwards, right? So there is two tendencies of the block. One is I had a value of P, but the block tendency is sliding down. It's just prevented. But I keep increasing the value of P. At one point of time, we see the tendency of the block is to move up. So there is a state where there is no tendency. That means there is no friction at the contact. So that would be a problem to think on it later on. But now the question is, what is the range of value of P, right? Here, so that this block is under static condition, under rest condition. That's the question. Determine the range of the word range comes because you rightly said if I keep increasing the P, at one point this will be moving up. So there is a state of this block impending to move up. There is a state of this block at the initially impending to slide down, not impending to slide down. It was sliding down, it was just prevented. Just prevented is an impending state. So from that point of value of P till another value of P, there is a range of value of P. This block is under rest condition. So you have to find out that range of value of P. Determine the range of value of P for the block to be in static equilibrium. Note, theta is greater than theta r, right? It was given. That is why you should have that in mind. In case theta is less than theta r, that means the block will be staying there only. Then you would not ask what is the range of value all, right? So the range of value here it is asked because the slope theta what I have drawn is already this angle is greater than angle of repose. So the block without an assistance of external force P cannot stay, it is under motion. So the application of P comes into the block so that the block motion down is just prevented. From there, the value of P can be incremented, and it can happen that the value will make the block to impend to move up. So these are the scenarios of this block. So if that is so, what is the range of value of P is what is the question. So did you get the problem? So can you solve this problem?
Sir?
Yeah.
Sir, but in this case, like in which direction friction would be acting, sir? Because
yeah, so that is what is the two conditions that you have to consider now. One is just prevented moving down, right? First condition is it is just prevented moving down. Second condition is impending to move up. So for both the condition, you should draw a free body diagram and you have to find out the expression for P. Is that clear?
okay, sir.
So let us consider first the body tends to move down, right? Tends to move down or just prevented to move down, right? Body, case 1. A block is just prevented moving down. So at that point of time, what would be my free body diagram? So I would have, see, drawing free body diagram, carefully listen and watch how do I do. I expect the same way you are doing it. If you follow the same manner, drawing the diagram, explaining in the examination, you would get the good marks. So this value is now W. And I would now draw the normal. Since there is no dimension involved, I take this is collinear with this, right? I was telling you the reason. So this is N. Now what is the direction of friction force? It is just prevented moving down, means the tendency of this would be coming down. So the friction force would be opposing this, right? Would be opposing this. This is the direction of friction force. So what is the value of friction force? 1 minute. So this is the direction of friction force. I take the smaller length of this. And look at now the important configuration. This angle theta. So this normal will have to the vertical also theta. So this angle also is theta. But now interestingly look at when I combine this friction force here. What is the value of friction force? Fs, right? So Fs, that is mu s times n. Mu s times n is what is there, right? So if I combine these two, look at the direction of the resultant. So this is the direction of resultant. So this is now happens to be R reaction, which is resultant of friction force as well as normal. And now this angle is what is friction angle. Correct? This angle is what is friction angle phi s. Look at theta is greater than phi s, which I was telling. Correct? So where angle of repose is phi s. So when theta is greater than phi s, this block is about to slide, and the impending state also that has to be ensured. So this is an impending state. So that's why it is mu s times n. Slight increase in slight increase, right? Slight increase in this. See, you would ask me. So this is supposed to be equal. Theta is equal to phi s. That is correct for an impending state. when only the block is there, but you have an assistance of P. That is why this angle theta can be greater than 5s and still it is under equilibrium. So another important force here is this P. Are you getting me? See here, you see this angle theta is greater than 5s. If P is not there, I say this block is just staying there, then theta is equal to 5s. Right? Then it is an angle of repose. But now theta greater than 5s, how then this can be under rest condition? Because of assistance of this force P. That is why this diagram comes like this. So if you have understood this, now I am going to take three forces equilibrium instead of considering this component. That's an advantage. The W, P and R. So I am going to look at only them. So I can conveniently redraw this free body diagram as a concurrent system of forces. So how do I draw? I'll draw a line represent the slope. I'll draw a line represent the normal. Now let me represent these three forces, and that would be easy to solve by applying Lami's theorem. So this is my load W. So I just slide, take the tail of the vector here. So this is my concurrent point, represent now this block. So this is W. So what is the direction of W to this? This angle is theta. Because this vertical will have to the normal the same angle theta. That is what you see here. That's theta. Now what is that angle of P? So P is at an angle alpha to the slope. So this angle is alpha. So now what is the angle of reaction R? Reaction R. So that is, so if I extend this line, that is, if this angle is theta, this theta. But now my R is less than theta to the normal, right? So my R would be somewhere here, like this. This is my R. It's not along that. Just draw 1 second. R is somewhere here. This is my R. This is R. So what is this angle? This angle is now theta minus phi. This angle is theta minus phi s. Clear? Any doubt? Ramesh Pandey? Rudranath?
No doubt, sir.
No doubt. So
Sir,
now see this,
sir,
yeah.
Sir, the angle between the P vector and the horizontal will be alpha plus theta, right?
Obviously, because this angle is what? Theta, right? This angle is
Yes.
theta. This is theta. So here this angle is theta, but I am not drawing that. So I just draw this so that now I have these three vectors concurrent. I'm going to use Lami's theorem and solve for P, right?
Sir,
Is it? Yeah.
so please once explain theta minus phi s.
Theta minus phi s. Look at here, what is this angle? This is phi s, which is reaction R to the normal. And vertical angle between vertical and normal is what? Theta. So this angle, whatever I represent, is to the normal now, right? Is to the normal or to the vertical? 1 minute. So this R to the normal is 5. I'm sorry. You are right. Who is that asked? Very good. Who has asked the doubt?
Satvik, sir.
Huh?
Satvik, sir.
Satvik, very good, excellent. So see here, whatever that I represented, this angle supposed to be to the vertical, right? See, look at here, this theta minus phi s is what is to the vertical. So this angle, what I have drawn, should go here. You are correct, excellent. So this angle should go here. This angle is what is theta minus phi s. Am I right? Whereas this angle is only phi s. Is it correct? Satvik?
Yes, sir.
So, yeah. Is it correct or?
Still a bit confused, sir.
Confused. I was also a bit confused now. Just a minute. Let me give you a clear cut idea. So this alpha is correct. This angle theta is normal to the vertical, correct. So I have just extended the vertical line. So what is the reaction angle to the vertical? So reaction or angle to the vertical is theta minus phi s. That's correct. This is correct. And reaction angle to the normal is what is phi s. That's correct. What is the doubt now? See, look at this diagram. If you are, see, why do I do that is to apply Lam's theorem. Now you look at here, look at this diagram, this diagram. So in this diagram, this is my R, right? This is R. So R to the normal is what is phi s. What is that angle between reaction and vertical? That is theta minus phi s. That's what is correctly marked. You are asking that, you are also saying this is correct now. And this angle is a reaction to the normal. So this black line, whatever I have drawn perpendicular to the slope, is normal. So what is the direction of resultant reaction to the normal is phi s. This is phi s. So what is the doubt now? There's no doubt, right?
Yes, sir.
Yeah. So now let us apply Lam's theorem. Right, so it's very simple. So what is that Lam's theorem state? If I have three vectors which are represented by a diverging vector from a concurrent point or converging vector to the concurrent point, you can write the ratios of the magnitude to the sign of angle included by other two vectors. So if I take vector P divided by other two vectors W and R, angle included by them, sign of angle included by them. So what is that angle? Sine. So look at from this itself. So R is on this side of the normal, right? So W and R, between W and R I should get the angle. So what is that angle I require is this angle I require. So this angle I require. So how do I get that angle? What is that angle? 180 minus. So look at this vertical. W is vertical. So this vertical line is 180. 180 minus this angle. 180 minus theta minus phi s. Correct? So that is
Yes,
what is. Yeah. And W divided by sine of angle included by P and R. So what is that angle? So look at now. How do you get that? I have here this is the right angle. This is the right angle, right? So 90 minus alpha. What does that I get here? Sine 90 minus alpha plus phi. Let me explain you if you do not get. 90 minus alpha plus phi. So 90 is what? 90 degrees here is this total. So in this alpha is there here and phi is there, phi s is there. So both should be subtracted. So this angle is right angle. This angle is right angle. What angle I needed here is from here to here. This angle is what I needed. So how do I get 90 minus alpha, 90 minus phi? That's what 90 minus alpha minus phi. So minus sign I have taken, this is that angle. So now I can get from these two ratios what is the value P required as W sine 180 minus theta minus phi s within bracket divided by sine 90 minus alpha plus 5s. Right? So now see, it's very simple to deduce further. So what is the sine of angle 180 minus theta? Sine of angle 180 minus theta is sine theta itself, right? Sine 30 or sine 150 is same. You can just check in the calculator. So W sine 180 minus angle is sine of angle itself. So theta minus 5s by. So sine 90 minus angle is what? Sine 90 minus angle is cos angle. So cos alpha plus 5s. Right? So this is the expression of P. So this value is the value minimum required value. Minimum means the lower range of my value. And in this itself, I can have different conditions. This direction of P not necessarily at an angle alpha. So the angle alpha to the slope for the direction of P is given to consider as a generic case. So this P can be horizontal, this P can be along the slope, or this P can be minimum value requirement. So if that is so, how do you go about saying? So let us have these three different cases. Three different cases now. It is case 1 for P to be P minimum. For P minimum, what is that I should have in this ratio? The denominator should be maximum, right? For P to be minimum, cos alpha plus 5s should be equal to 1. Maximum value of cos of angle is 1. If that is so, alpha plus 5s should be equal to 0. So alpha should be minus 5s. So this is the condition. Alpha should be minus 5s. Right? So if I substitute that in this, what would happen? This is going to be 1. So P minimum value is going to be W sine theta minus 5s. So what is P minimum here? That's the minimum value of P just required to hold the block sliding down, preventing it sliding down. That's a expression. That's P minimum required. Now, if P to be horizontal, so what is the condition? What is the condition? So you are saying that P direction from the slope is alpha, slope is angle theta. So P to be horizontal, alpha plus theta should be equal to 0, right? So alpha will be minus theta. That's the condition. If alpha is minus theta, now my expression in this rectangular box would be changed. So putting this in this equation 1, this is Roman letter 1. So this is equation 1. So putting this in Roman letter 1, what do I get? So if I substitute alpha is minus theta, cos of theta or cos of minus theta is one and the same. So I would have now P would be W sine theta minus 5s by cos alpha plus 5s. So if I put this minus theta plus this, so minus sign, if I take cos of minus angle is same as cos of plus angle. So I can rewrite here as theta minus 5s. So sin by cos stands for W tan theta minus 5s is what is P to be horizontal. This is my equation 2. I am having this one block playing around and going to generate 6 problems independently. So these are the expressions. So now P to be along the slope, for P to be along the slope. What is the condition? Alpha should be 0. That's all. So then alpha should be 0 means it will be along the slope. So then my expression of P along slope would be equal to, in this expression, alpha 0 if I put, that's going to be W sine theta minus 5s by alpha 0, so that's simply cos 5s. That's my expression 3. So these are 3 different possible cases that's possible. So now my question now, let me go back to the statement of the problem. Determine the range of value of P. Range of value of P minimum, if I ask, you should take first formula, right? Range of value of P to be horizontal here, then the second one. If P to be along the slope, then the third one. So you have found now 3 cases only for the first case. A block is just to be prevented moving down, right? So now, what is the upper value of this range? A block has to impend to move up. So that's what you have to work out. So do you have a class next period?
Yes, sir.
Yeah. So I leave it to us homework. Otherwise, we will continue in the next class getting that. Hopefully, you will be able to solve. So only thing is, in that free body diagram, this friction force, whatever is appearing, would be in this direction. So you see that your reaction to the vertical is not theta minus 5s instead of theta plus 5s. And the expression would be changing accordingly. So draw the free body diagram and try to get in the similar approach the upper value of this range, and then you have with you the answers of 3 categories depending upon the direction of application of force P. And that is what I just to stop at this point and ask you as a homework to complete, and we will meet again tomorrow 1:30. It is the Monday timetable, right? Tomorrow is an instructional day. Today we have received a mail reminder from Dean Academics. So let's meet tomorrow as usual, Monday 1:30. I have already sent the necessary meeting link in the channel, lecture channel. So you can join through that, and we will have tomorrow again continuing with this problem. Then we will get into another interesting group of problem called wedge friction problem. So that's what is tomorrow's lecture's agenda. So is that fine? Do you have any doubts of today's lecture? You can ask. Otherwise, I would download your attendance sheet and end the meeting for all of us. Any doubt? Yes, Venkat.
Sir, I thought the class was from 4 to 5, so I joined a bit late, so please consider that.
Yeah, that's fine. I do not exactly look at the time stamp. I sometimes look at, and if it is last minute or somebody joined, I do not give the attendance. Otherwise, fine. Okay. So tomorrow, don't forget, we have class at 1:30.
Yes, sir.
Okay, yeah.
Thank you.
Yeah, fine. So stop recording.
Sir, this problem can also, we can also obtain the equations by using fx is equal to 0, fy is equal to 0, right, sir? Similar equation.
Yeah, obviously you can do it. See, I have purposely did today's problem applying Lamis theorem because wedge friction problem is what we are going to solve. You'll see that application of Lamis theorem is quite easier. You'll avoid a lot of mistakes. And also I was interested to get this conditional problem explanation, P to be minimum, P to be horizontal all. So that would become easier if I have my trigonometric terms coming like this. No, all in one go. Maybe I have taken more time to explain you, but this is faster way of doing than considering individual components, than doing by condition of equilibrium, right? You can make an attempt like that.
Yes,
Both are of
Yes, sir. Yes, sir.
complementing methods. But I purposely wanted to solve this by Lamis equation because I would appreciate and insist you to solve wedge friction problems whenever 3 forces are in the block by Lamis theorem, right?
Yes,
Is that
sir.
fine? Yeah. Okay. There is no more question. I will stop recording.